So we're going to wrap up 1.1 with this last video segment, and let's just summarize where we're at right now with solving systems of linear equations. To solve a system of linear equations, we will apply what are called elementary row operations to the augmented matrix. And here are the elementary row operations. There are three of them. Number one, add a multiple of one row to another row. Number two, multiply a row by a non-zero constant. And there's a third elementary row operation where we interchange two rows. We did not use this third one in the preceding example. We'll see that used very soon. So note, elementary row operations are reversible. If row operations take us from a matrix A to matrix B, then we can use row operations to get from matrix B back to matrix A. That's going to be important later on. Two matrices are said to be row equivalent if one can be obtained from the other through elementary row operations. So if two augmented matrices are row equivalent, they represent systems with the same solutions. Now we're going to do one more exercise here. Let's determine if the following system is consistent, and if so, find a solution. There are three equations here, and there are just three variables involved. So we're going to go ahead and let's set up the augmented matrix for this system. So I'm going to set up a matrix with the first column being the coefficients of the x1 variable. That's 0, 2, -1. Then the second column is going to be the coefficients of the x2 variable, 1, 4, -1. Then the x3 variable, 5, -4, 7. And then the last column will be the constant terms that are always on the right-hand side of the equal sign. So we need this standard form to be able to set up the last column, -1, 6, -1. And now I'm just going to go ahead and start applying row operations to get this matrix into its echelon or reduced echelon form. When I look at that first column, you know, I want a 1 in that first position. I'm trying to get a 1, 0, 0. So I don't want 0 in that spot. So what I'm going to do here is, this is the first time I'm going to use number 3 of the elementary row operations. I'm just going to interchange row 1 and row 2. You could also interchange row 1 and row 3 if you wanted. So that's the symbolism I'll use for that. So that's also a legal move here. And so row 2 becomes the first row, 2, 4, -4, 6. And then I have 0, 1, 5, -1. And as far as the equations are concerned, that just corresponds to switching the equations around. The equations certainly don't care what order they're in. And then I like to get a 1 in that position. The textbook says sometimes they leave that for later, but I like to get the 1 in that top position right away. So I'm going to replace row 1 with 1/2 row 1. So I have a 1, 2, -2, 3, 0, 1, 5, -1. negative 1, negative 1, 7, negative 1. So only the first row has changed. And now I want to get a 0 in the first position of this last row, right? I want 1, 0, 0 coming down the first column. So row 3, I'm going to replace with row 3 plus row 1, because if I just add this 1 to it, it will become 0. So 1, 2, negative 2, 3, 0, 1, 5, negative 1. And then I'm going to add row 1 to row 3. So I get 0. 2 plus negative 1 is 1. Negative 2 plus 7 is 5. 3 plus negative 1 is 2. So now I'm happy with my first column. I move down diagonally. I'm happy because I already have a 1 in that position as I come down diagonally. So now I want a 0 below. So I'm going to change row 3. I want row 3, I'm going to just subtract row 2, or add negative 1 times row 2, if you will. And I have 1, 2, negative 2, 3, 0, 1, 5, negative 1, 0, 0. I'm going to get 0, correct? And then I'm going to get, let's see, row 3 minus row 2. 2 minus, I think that's 3. Now, I got 1s with 0s below, 1s with 0s below. Now we haven't seen this situation yet. If I come down to a row, this 1 is the first position of the first row. Then this 1 is the first non-zero position of the second row. Sometimes as I come down trying to get my rows in position, I don't go strictly diagonally. If I have all zeros leading up to a certain point, I have to go to the first non-zero position. So I'm now going to move all the way over to this 3. I'm going to bypass that third column because there's a 0 in that position. I move over until I hit the first non-zero number. And so row 3, I'm just going to replace with 1/3 row 3 to get a 1 in that position. 1, 2, negative 2, 3, 0, 1, 5, negative 1, 0, 0, 0, 1. And so we call this our echelon form. Now this is not a reduced echelon form yet, but I'm going to finish up the problem right at this point, because now this is something we have to learn to recognize. This last row, we have a row of zeros followed by a non-zero number, followed by a 1. This corresponds to the equation. This is like saying 0x1 plus 0x2 plus 0x3 equals 1, or 0 equals 1, which is, of course, a false statement. 0 doesn't, you cannot say 0 is equal to 1. Or you could just say it's impossible. We have to learn to recognize that. Whenever we have get to a point where we have 0 equals a non-zero number, then there is no solution to the system. And using the language of our course, we would say the system is inconsistent. I'm fine if you say no solution or inconsistent. And So this is the first time we've seen this, and it's always going to pop up in this way, with the augmented matrix having all zero entries except for the last column, the constant term column, which is non-zero. That stands for a false equation that's impossible. Since that's impossible, the system has no solution. And that's the end of 1.1 finally. Again, we're going to delve deeper into this in 1.2, so stay tuned.